I've got good news and I've got bad news. I'll do the bad news first. The bad news is that we have no idea what alien life, intelligent or otherwise, might look like. Seriously, no clue. Your guess is as good as mine. We have no data, no evidence, no images, no spectra, no secret Santa gift boxes, nothing. We don't know what aliens look like. And this is the real kicker. We're not even confident that we can identify them if they did exist. So that's a bummer. But the good news, however, is that we have a lot of options. We won't be able to come up with a firm answer, but that's okay because those options are really fun to talk about. So let's talk about what aliens might look like. Where should we start this conversation? Well, why not science fiction? I mean, like I said, it's not like we have any evidence to go from, so our imaginations are as good a place as any. And when it comes to science fiction depiction of aliens, we have the full spread. On one hand, there's the usual TV alien that is very much a human being with some makeup on, which I understand is a product of budget and time constraints. And then on the other end of the spectrum, there are those aliens of the week that are some weird energy being floating in space or a puddle of goo in a cave somewhere on some random planet. My point is that if we can possibly imagine it, then it just might be a candidate for aliens. It's wide open here. We actually have no idea. And considering that the Milky Way galaxy is home to a few 100 billion stars with up to a few trillion planets, and that's just one galaxy amongst trillions in the observable universe and countless more beyond that, it's somewhat reasonably likely to me that if life is possible, and life is certainly possible because, hello, then there might just be room for all the kinds of creatures that we can possibly imagine. But what about the majority of aliens? Are we, like human-type creatures, special? Are we unique? Or are we common? Are we boring? What's a typical alien look like? Well, here we can boil it down to two choices. The typical alien is either a lot like us or not. So let's start with the argument that aliens might just look like us. Let's see where this goes. Let's see how compelling it is. Well, human beings and all life on Earth are built from very common elements. I mean, physics is physics, chemistry is chemistry, biology is going to be biology. There are only so many elements on the periodic table. There are only so many ways to combine them, and they only participate in so many chemical reactions. Yes, it's a large number, but when you boil it down to the most common elements in the universe, you don't get a lot of options. And you know what? People, human beings, life on Earth, we're made of the most common elements. Like look at us, we're water. And what is water? Hydrogen, which has been around since the Big Bang, and oxygen, which is formed in the hearts of sun-like stars, and sun-like stars are super common. There's a lot of water everywhere. It's not special that we're made of mostly water. What else do we use? We use carbon. Well, that's made in sun-like stars too. So great, easy carbon, tons of carbon everywhere. Sulfur, phosphorus, nitrogen, all of these are made in more massive stars, which means they're rarer elements for sure, but also not super rare. You know, the 5 elements that life on Earth needs to survive, carbon, oxygen, sulfur, phosphorus, hydrogen, are super common. Water is the most common molecule in the entire universe. Oxygen is the most common element on the Earth. There's some of it in the air, either as oxygen, oxygen, or carbon dioxide. A lot of it is in rocks with silicon dioxide. Pick up a handful of dirt, you're holding a bunch of oxygen. There's nothing super special about the way we are built. And with that set of elements, there are only so many biochemical pathways to generating and transferring and storing energy. It's kind of it. But that's just basic chemistry and biochemistry. What about, our body plan? What about us as humans and how we look? Well, we can probably assume, and this is an assumption for sure, but we're going to go ahead and make it for the sake of this argument, that we have a typical evolutionary pathway. Evolution is dumb. It doesn't have a program. It doesn't have a plan. It doesn't have a goal. It just happens. Once life gets going, evolution just happens to it. And you end up with all these varieties of creatures that are adapted to fill various niches. And so our evolutionary pathway led us to, say, breathing oxygen. Why? Because oxygen is A, really common, and B, really, really good at storing and transporting energy. We didn't evolve to breathe vacuum. I know that's an oxymoron, but that's my point. We evolved to breathe oxygen because it's really handy. Like, evolution is probably going to favor the most energy efficient pathways available. So there's nothing super special in that direction. Our star isn't all that special. It's not the biggest star. It's not the smallest star. It's somewhere in the middle. It's pretty calm. There's lots of stars like the sun. Our planetary environment is rather generic, not common, with liquid water on the surface and the habitable zone around a star. Like, okay, that's not the most common planet in the galaxy, but it's also not super rare. Very rough estimates, and these are very, very rough estimates, say that there are somewhere around 5 billion Earth-like planets around sun-like stars in the habitable zone. 5 billion! Yeah, that's not the most common thing in the galaxy, but still, when you have 5 billion of something, you got a lot of something. Our environment isn't all that special. There are only so many ways to build a body. If you want to move around, you need like some sort of limbs to move around. If you want to acquire energy, don't we all? You can either choose to stay put and let it come to you, or you can go after it. And as soon as you want to go after it, and I'm putting like anthropomorphizing evolution here, please forgive me. If you're a creature and you want to go after some energy, you need to move around. There are only so many ways to move around. If you want to interact with your environment, there are only so many ways to interact with your environment. You can grab it, basically. That's it. That's your choice. And if you're going to look for energy, you need to look for energy. You need senses. It's very efficient to have all your senses clustered in one place. We call it the head, or at least the majority of your senses. It works for this body plan on Earth. It's probably going to work somewhere else. Chemistry is chemistry. Physics is physics. You want to access the universe around you? What are your choices? Electromagnetic waves, pressure waves, tactile responses, smells, so you can pick up all the interesting chemicals floating around in the air or water. Like that's it. Your choices are limited here. And if you're going to build a body, there are only so many ways to send signals from one body part to another. If I want to tell my hand to move to grab that piece of food, there are only so many ways for me to tell my hand to move. Likely I'm going to have something like a nervous system. Likely I'm going to have some version of eyes and ears. Likely going to have some version of hands or tentacles or clamps, teeth, beak for consuming resources. Our body plan is probably rather typical. We're pretty mobile. We're pretty efficient. We're taking advantage of all the most common resources around us. When it comes to intelligence itself, it's difficult, we think, to gain intelligence in water because you have no access to fire, which was a big deal for humans. We have a relatively calm environmental situation here on the Earth. So likely other intelligent species also have a relatively calm environmental situation. Intelligence is probably unlikely to arise in prey animals. They're too focused on not getting eaten all the time. Pretty simple thought patterns there. Please don't get eaten. Please don't get eaten. So if we were to meet aliens, maybe they wouldn't look exactly like us, but we could probably map alien parts one-to-one onto human parts. And because we're all trying to ultimately solve the same set of problems. We all arose from a similar set of evolutionary circumstances with a similar set of base organic compounds, same set of challenges, same evolutionary pressures. I don't know, maybe the cheap TV sci-fi alien with some makeup on their forehead isn't that far off. Maybe aliens look a lot like us. And hey, you know what? The benefit of aliens looking a lot like us is we would know what we're looking for. When we go to search for aliens, we have no idea what aliens look like, but if they look like us, smell like us, talk like us with radio emissions, that's a lot easier to spot than some like energy being floating in the cosmos. We won't even know it if we saw it. More on that later. So maybe that's it. That's like, maybe aliens just look like us and that's it. Or not. Maybe life is nothing like us. Or any kind of life, past or present on the earth. Maybe we are weird and special and different. Maybe life out in the cosmos is just super weird. And what we've experienced on the earth is just the tip of the iceberg. Or maybe it's the reverse. Maybe we're the weird ones. Maybe aliens have been observing us from afar going, can you believe what is going on down there? Let's stay away from that. Look at them walking around. Look, the truth is we have no firm definition of life. There are over 200 different definitions in the literature. I, of course, have my favorite definition. And it's my favorite definition because it's so simple and so broad, and I don't have to pretend to be a biologist to explain it to you. And the definition is this. Life is that which contributes to Patreon. That's patreon.com/pmsutter. If you want to consider yourself alive, please go to patreon.com/pmsutter. And I'm still running the special for my new book, Rescuing Science, Restoring Trust in an Age of Doubt. If you contribute at $25 a month or more, you get a free autographed copy sent right to your doorstep. And then you can cancel right after that. It's fine. I just want to get the copies out there. I appreciate it. Okay, the real definition. Life is anything in the universe that is subject to Darwinian evolution. Life is that which evolves. It's not a perfect definition. We still get to debate about, say, viruses. But it's useful for us because in this episode, we're exploring the maximum variety of possible life forms. And so it's handy to be as general as possible. On Earth, this evolution is achieved with a three-part combo of DNA, RNA, and proteins. DNA stores genetic information, RNA transcribes that information and creates proteins, and the proteins get work done, including replicating DNA. These all work together to allow the DNA to interact with its environment, to influence it and be influenced by it, and then make changes to itself through the process of evolution. This process of evolution on the Earth, we are alive because we evolve. It needs a power source. You need something running behind the scenes to power all this. It's largely powered by the sun, with various kinds of chemical reactions used to store, transport, and release energy. So when you eat a cheeseburger, you're just consuming repurposed sunlight, which is kind of cool and also very delicious. But if we're going to be as general as possible in exploring what life could be, then you don't need this exact same combo to make evolution work. You definitely need an energy source. You can't get around that, but it doesn't have to be the sun. Some life on Earth doesn't even use the sun. It can be any kind of energy source you want. And we have a very complicated arrangement of DNA, RNA, proteins all working together in a circle to make evolution happen. There can be all sorts of interesting chemical tricks. All you need is a certain level of complexity in your interactions, in some way to store information and interact with other chemicals, with your surroundings, and then evolution can take place. Because as soon as you start influencing your environment and being influenced by your environment, and you have the ability to make changes to your own information and pass that on to a new generation, you get evolution. And so anything that satisfies these basic requirements, if you have an energy source and you can experience evolution, then you are alive. And this allows us to widen the lens of what life could be in the universe. So let's start with the relatively benign on the weirdness scale in terms of the varieties of life that could exist in the universe. Let's start with life that exists permanently under ice. There are these outer moons in the solar system that orbit the gas giants. I'm talking Europa, Enceladus, Callisto, Pluto might be up there, Triton, Titan, all of them, like a whole bunch of them, are covered in a layer of ice. And then underneath that ice, we believe, is a layer of liquid water. In fact, there's more liquid water on almost any of these moons. Like Europa has more liquid water than the Earth does. In fact, it is the most common source of liquid water in the solar system, and therefore probably the galaxy, and therefore probably the universe. If you want to ask, where's the liquid water? It's not on the surface of planets close to their stars. It's locked underneath icy moons. So liquid water is really, really great for life on Earth. Liquid water acts as a solvent. It's a place where we can have it's just a bath where we can have chemical reactions, a playground for us. Us land creatures are just bags of water that we carried from the ocean onto the land. That's why we have skin, so we can keep our water inside, and we can do all of our interactions in that salt water that we evolved from. So yeah, liquid water. Downside to these icy moons is they are completely and permanently locked off from the sun. They never see the sun. So they can't use the sun. They can't use photosynthesis as an energy source. Okay, that makes things more challenging, but you know what? There might still be energy sources there, especially deep sea vents, like volcanic vents at the bottom of these oceans. That supplies some energy for some life on Earth. They never see the sun. They don't use photosynthesis. They just use the heat and chemicals pouring out of these vents. Maybe that happens on Europa too. And who knows what that life might look like. Remember, the deep sea creatures on Earth likely started out in shallower parts and then evolved into the deep sea environment. But what would life be like if it never had any other option? Would intelligence arise? Would it even understand the universe the same way we do? Would they even need eyes? Would eyes ever evolve? Maybe, I don't know. What about different kinds of planets? Let's keep going on the weirdness scale. What about like super Earths? Huge planet, large gravity. What if there's liquid water on the surface of those worlds? Would things be bigger, smaller, the same? It's impossible to say, especially given the tremendous variety of life on Earth. But it's fun to think about. What about these hypothetical Haitian worlds? These are planets larger than the Earth, covered in liquid water, so globe-spanning liquid water oceans, and then surrounded by a very thick hydrogen atmosphere. They have a surface, technically, but no access to the sky, no land, just a world of water and hydrogen. Maybe it's brighter sometimes, and then darker sometimes, but the atmosphere is so thick you don't actually see the sun itself. You certainly don't see the stars. What would be happening in those worlds? What interesting biochemistry might arise? Even if it's sourced from the same compounds, the same elements as life on Earth. Let's say you're still working with carbon, oxygen, sulfur, phosphorus, nitrogen, the basic five. What if there are other ways to combine those? What if there are other interesting pathways? There's nothing obvious that we've discovered, but also we're kind of biased here. Because of our own biochemical pathways, we have this incredibly rich system that powers our life, that powers our evolution, a system so complex we've barely begun to scratch the surface. What if there are other pathways to storing information, storing and transporting energy, interacting with the environment that we haven't even thought of yet, that's playing out on some alien world? You may not even need a surface. What about the gas giants? The interior of Jupiter has all the same elements that the Earth does, and a lot more of everything, for that matter. And it has a source of heat. It's super hot on the inside of Jupiter and super cold on the outside. There's heat transport. It's not powered by the sun, it's just powered by Jupiter's own heat. More than enough energy to power evolution, and all the right chemicals present. What if there are creatures submersed in that thick atmosphere, 1,000 miles below the surface? What kind of exotic chemistry games do they play? What would intelligence be like if it never saw the stars, if it was on a Haitian world, or locked under the ice, or buried inside a gas giant? What would they think about the universe? Would an intelligent creature even conceptualize the universe the same way we do? You don't even need water. Let's get a little weirder. You don't need water.
Water is for cowards. Water makes you weak.
Water is the solvent for all life on Earth. It's the bath that all our chemicals play in to do the life thing, but you don't need it. Water is handy because it's super common, but it's not the only thing that can be a solvent. It's not the only thing that can be a playground. What about methane? Methane isn't as common, for sure. It's not as handy, for sure, but it does remain liquid at far lower temperatures than water does. So this allows more pathways for life. Like the big example here is Titan, the biggest moon of Saturn. There are lakes and oceans of methane, liquid methane on the surface of Titan at something like, negative 270 degrees Celsius? Far too cold for liquid water. In fact, the crust of Titan is frozen water. And then there are seas of methane on top of it. There's rain of methane. This is the solvent. It's a liquid, which is maybe good enough for life. Maybe there are entire pathways to solving the energy problem, to acquiring energy, storing it, using it later, all using methane, all operating at temperatures that any life on Earth, no matter how extreme, would be killed instantly. There's even research, I saw some research recently, about the potential of life in giant molecular clouds, where you get these dust grains floating in interstellar space, and then the dust grains are coated in a layer of ice, and then there's methane sprinkled in that ice, and then they get hit by UV radiation, by cosmic ray particles, and this can provide a source of energy. And then there are chemical pathways that allow these molecules to store and transport energy and possibly have methane-based life, not even near a star. That life would be truly alien, presumably because it'd be so cold, it'd be much slower than us, much more basic than us, because here, sitting on our warm Earth, there's a lot more energy available. There are a lot more chemical games you can play with all this energy just swimming around in the sunlight. You get far fewer pathways out in a giant molecular cloud in interstellar space. But there aren't zero pathways available. There are so many games you can play with swapping out our chemistry, because you can pretty much take any part of our biochemistry and find elements that play similar roles. Sometimes it's the simple one-for-one substitution. Other times you have to build entire parallel pathways. Like, for example, you can swap out water for methane and get alternate pathways to life, to potential life. You can swap out the methane for hydrogen fluoride, which would kill you and me very quickly, but might be just the thing for the basis of biochemistry in another world. You can swap out carbon for silicon. Silicon can also make large molecules bind with many other elements, just like carbon can. It's not as sturdy, it's not as hardy as carbon, but it still works. Phosphorus, you can swap it out for arsenic. Plays a very similar role in biochemistry. Instead of hydrocarbons, which is like most of our bodies are built on water and carbon in various complex arrangements, you can have instead boron and nitrogen combinations, which would literally explode on the Earth, but maybe not elsewhere. You want rock monsters? We've got rock monsters. Silicon dioxide, dirt, when molten, like it is in the Earth's mantle, could provide the basis for life, because there's a source of heat and there are complex chemical interactions, and then all the ingredients you need. Maybe there's some strange form of life buried like 100 miles down in our mantle. I don't know, but it's fun to think about. Let's get weirder. Let's go back in time. All the examples and options I've given so far have been about the present day universe, the modern universe. But the modern universe, our chemistry, our elements are based on multiple generations of stars living and dying in the universe. You get sun-like stars, they die, they explode, they spew out carbon and oxygen. You get bigger stars, they explode, they spew out phosphorus, iron, nickel, sulfur. You get even bigger stars, you get the rest of the periodic table. You need multiple generations of stars in the universe in order to build something like the Earth, because you need to wait to have enough oxygen, enough carbon, enough water, enough phosphorus, enough nitrogen to make it worthwhile. So everything I've talked about, all these alternatives to biochemistry, have relied on multiple generations of stars, but the universe has not always been this way. We can push the clock back. And that opens up the possibility of some very strange creatures. Like, I don't know, remember, all you need is a source of energy and then enough complexity that you can potentially store information and pass it on from generation to generation. That's how you get evolution. If we go back to, say, the cosmic dawn, before the cosmic dawn, before the first appearance of stars, yeah, it was dark eventually, but for a while it was warm. The entire universe was heated by the cosmic microwave background. Eventually, the cosmic microwave background cooled off, and the universe did become dark, and then stars appeared. That took a few 100 million years. What about the first million years, 1,000 years, where the universe was heated, warm, more than warm enough, more than enough energy floating throughout the entire universe? And sure, chemically, there's only hydrogen and helium and a little bit of lithium. Maybe there's some interesting games to play there that we haven't thought of yet. What about the first black holes? Life in a black hole would probably be miserable, but because black holes are such intense engines of gravity, light, any kind of starlight or cosmic microwave background, as it approaches the event horizon of a black hole, blue shifts up into incredibly high energies. You can actually hang out near the event horizon of a black hole and have more than enough heat to do whatever you want, simply from light falling in and getting blue shifted. I don't know. I'll be the first to say I don't know what life could even possibly, how it could even possibly be constructed near the event horizon of a black hole, but we've got energy. And where there's a lot of energy, there's the potential for complex arrangements of whatever, and there's the potential of life. Speaking of complex structures, some people have investigated the possibility of life inside of neutron stars. Neutron stars, these balls of ultra-dense matter, essentially giant atomic nuclei, their interiors are massively complex and we do not fully understand it. But we do know one thing, that their interiors are very complex and spontaneously complex structures arise. These things are small, like micrometer small structures, but they're structures and they're complex. Maybe they do a little dance. There's plenty of heat. Neutron stars are really warm. And with all those neutrons crammed together, they can spontaneously form very complex, interesting shapes and arrangements. Maybe that's all you need to get life started. And heck, what about dark matter and dark energy? Like I said, let's get weird. 95% of the universe is of a form unknown to physics. We have no idea what dark matter is, and less idea of what dark energy is. There are ideas floating around out there for dark matter that there is an entirely parallel or mirror set of periodic table for dark matter. That there isn't just one dark matter particle that's swimming through every galaxy. There's like 200 of them. And then, in fact, for every particle, like every electron, there's a mirror electron in the dark sector. There's a mirror quark. There's a mirror neutrino. And that there can be all sorts of forces operating within the dark part of the universe, within dark matter, all these different kinds of dark matter that are totally independent of the visible universe. They just operate. There could be like a dark matter Earth, like right over there, doing its thing, and we wouldn't notice because it's literally invisible. I mean, there's a huge playground here, isn't there? Like, it's just, if dark matter can do anything at once and it be invisible to us, maybe there's dark matter intelligence. And they can't see us the same way we can't see them. They're dark, they're invisible to us, they don't interact with light. We are the light portion of the universe. They can't see us. Photons from us just sail right through them. They don't even know they exist. Those photons exist. We're invisible to each other. Why not? What about the first moments of the Big Bang? Physics got a tiny bit complicated in the earliest moments of the universe. Things were a little bit hot, so you have an energy source and you have the opportunity for complexity. It would not be chemistry, because there's no chemicals yet. It wouldn't even be atomic physics, because there aren't atoms yet. These would be like fundamental like sub-fundamental particles, double fundamental particles, like cosmic strings, like magnetic monopoles, like exotic structures that can form very complex arrangements. So there you go. You have an energy source and complex arrangements. Now, if that life arose, it would last for less than a second. Remember, all you need are complex structures that can interact with the environment and replicate themselves. Add in an energy source and bam, you have the potential for Darwinian evolution. It's fair to say that the breadth of possible, and I'm stressing the word possible here, options for life in the universe go far beyond our imaginations. But if you're ever curious, if you want to get a taste of the variety that life could have in the universe, if you just want a little taste, well then just look at the Earth. Nature is very creative. Yeah, we've got the familiar animals like people, dogs, cows. 4 limbs, a head mounted on a neck, eyeballs, ears, nose, mouth, etc. But then there are some critters with more than 4 limbs. And then there are critters with not bilateral symmetry, like mirror left-right symmetry, but 6-fold symmetry, stony corals, sea anemones, thousands of species with completely different body plans. You've got the octopi, no wait, it's not a Latin word, octopus. Let's go with octopodes. They're wild. They've got separate small brains in each tentacle. Imagine your arms and legs literally having a mind of their own. You've got the star-nosed mole that looks like it took a grenade to the face. You've got aquatic animals so highly adapted to the pressures of deep sea that when you haul them up to the surface, they just turn into gelatinous goo. You've got the platypus, which really can't decide what kind of animal it wants to be. There's a lot going on Earth. And don't even get me started on all the microscopic creatures. Don't think too much about the tiny dragons living in your eyebrow follicles, or the mites constantly crawling across your skin eating dead skin cells, or the fact that with every breath you're inhaling all manner of bacteria and spores and ugh. The presence of life on Earth even stretches the very definition of life. Are viruses alive? They mindlessly replicate and consume resources, but they need a host to survive. Does that disqualify them? I don't know, the same thing can be said of teenagers, and so the debate continues. What about prions? These are collections of proteins that act as pathogens, fully transmissible. There's no DNA, but they kind of sort of act alive. We've observed life in almost every possible biome on Earth, from the depths of the ocean, to buried under Antarctic ice, to multicellular creatures living 2 miles below the surface of the Earth, or floating in the upper reaches of the atmosphere. And that's just modern day life. Evolution has had 4+ billion years to experiment with life, and at this point has tried pretty much everything. I mean, dinosaurs? What hallucinogenic nightmare cooked up those? And during the Cambrian explosion, when large multicellular creatures were first getting going, you end up with animals that just have random body parts attached to them to see what works out. And then, oh right, there's the archaea, this entire kingdom of life, these little critters that will eat just about anything. Some of them photosynthesize, some of them directly use oxygen, some of them use carbon as an energy source, some of them use methane as an energy source. Seriously, if there's an energy source in the environment, then there's likely an archaea microbe ready to eat it. We've barely begun cataloging the archaea because they sit so far outside of known biochemical pathways that sometimes they're hard to spot. We just think it's like some random chemical process. Turns out it's a microscopic critter. And if we push back to the very origins of life, then by definition it gets weird. Why? Because at some point deep in the past, the Earth was very much not alive. And then sometime later it was. And there was a transition from non-life to life, and that was a very complicated time, where molecules dancing together went from regular chemistry to biochemistry. And there was necessarily a lot of gray area that stretched the definition of life as we know it. And were a million, I'm guessing, possible directions that early life could have gone in. My point here is that if we want to study aliens and try to understand what they might look like, what body plans or adaptations or chemistries they might have, how they might sense and interact with the world, perhaps we don't have to look very far. Yeah, we can imagine energy beings in the dawn of the Big Bang. We can imagine dark matter, intelligent creatures wondering why they're so alone. Unless those are the gremlins that keep stealing my socks. I don't know, the jury's out. But here on Earth, in terms of chemical-based life, water-based life, we've got it all. When I present these kinds of debates, I usually don't take a stand, but the more I think about it, the more I think we're barely scratching the surface of what life could be, even when we push the limits of our imagination. And this gets me thinking. We can imagine all sorts of different kinds of aliens. But are there limits to our imagination? Listen, I want to share something with you. This is my own personal conspiracy theory. This is backed up by no evidence whatsoever. And this isn't even a firm scientific thought. It's just a fun thing I like to imagine late at night when I look up at the stars and I wonder if we're alone or not. So please, feel free to quote me on what I'm about to say. But if you do it with all the caveats that I'm not entirely taking this seriously. It's just a fun thought experiment. It's a fun, seed for imagination. Here's what I like to think sometimes, between you and me. When I think about life in the universe, I wonder if it's right there, right in front of our noses. Common, prolific, abundant, but it's of a kind that we can't discern. Imagine you see a trail of ants, walking in the forest, and you step in their way, and they encounter your shoe, and they see this impassable wall, and you see them, they navigate around it and continue on their way. To them, they saw a barrier, just one more thing in the universe that got in their way, whatever. Okay, let's just go around it, go on with our business. You had a different perspective. You were a human. You were another living creature. You interfered with them. You could see from a different perspective. The ants didn't even see a shoe, let alone the intelligent creature behind it. They just saw a part of the universe and moved on with their lives. They were limited. What if we're the ants? What if we're limited to our earthbound brains, the product of our evolution, our senses, our own intelligence? We're very creative creatures, but we can only see the world in a certain way. We literally can't conceive of other ways to examine the world. So what if, and I remind you, this is just for fun, what if the universe we see isn't, the universe we see? What if we look around at an empty cosmos full of wonders, but are forced into a limited perspective? Aliens are always a bad hypothesis when we see some mystery in the cosmos, saying it's aliens. That's always not a good scientific hypothesis. That's not what I'm talking about. What if there is some form of life or intelligence that we truly, fundamentally can't fathom? Not just like dark matter life, but things we can't even conceive of. What if life in the universe is invisible to us? Invisible to our perception, invisible to our understanding, blocked from sight by our own genetic heritage. What if aliens are right there and we don't know it, and we can never know it because we can't see them for what they are? This thought strikes me with fear that we'll never fully understand the cosmos and that we'll never be clever enough to identify aliens that are out there. But it also comforts me, because when I look out at the vast expanses of the universe with the light years of nothingness between the stars, I sometimes shiver, and I don't want to be alone. Thank you to Ollie I on Facebook, Maddie A on email, Billy M on email, and Brandon S on email for the questions that led to today's episode. And thank you to all my top Patreon contributors. Thank you to all my Patreon contributors. That's patreon.com/PMSutter. My top ones this month are Justin G, Chris L, Barbara K, Alberto M, Duncan M, Corey D, Nyla, John S, Joshua, Scott M, Rob H, Lewis M, John W, Alexis, Aaron J, Gilbert M, and Valerie H. I sincerely can't thank you enough. And if you subscribe to Patreon at $25 a month or more before March 31st, I will send you an autographed copy of my new book, Rescuing Science, Restoring Trust in an Age of Doubt. Keep those questions coming. I love your curiosity. I love doing these episodes. These episodes are powered by your questions and your questions alone. That's askaspaceman@gmail.com, or check out the website askaspaceman.com. You can also follow me on all social channels. I'm at Paul Matt Sutter, and I will see you next time for more complete knowledge of time and space.